We have learnt about the equation of motion of simple harmonic motion in previous lecture, and you have seen actually the equation of motion of SHM is a second order ordinary differential equation with constant coefficient, and you have obtained this equation in previous lecture. So here I have written this very equation directly. Now in this present lecture, our aim is to solve this differential equation, okay? And for this I have considered there is an oscillator or a particle of mass m performing or executing simple harmonic motion on this straight line shown in this figure about the equilibrium position O, okay? At any time t, we have assumed that the oscillator or the particle is at this point P when its displacement from its equilibrium position is x, okay? And you know the differential equation of simple harmonic motion in this condition is written as d2x dt square plus omega square x equal to 0. And you have seen earlier that this omega square has been written in this equation instead of k over m, where k, you know, this is force constant and m is mass of the oscillator. And so you can say that this omega is equal to a square root of k over m. All these things we have learnt in the previous lecture. And you also know this omega is what? This is actually the cyclic or angular frequency of simple harmonic motion, okay? Now, as I have told you in this present lecture, our aim is to solve this differential equation. When you say that we have to solve this equation defined in equation 1, it means you have to find this x, which is displacement of the particle, as a function of time. So what is our aim? Our aim is to find what will be x of t. This is our aim to find in this lecture. It is a very simple differential equation, and we can easily solve it. As you can see, since this is a second order differential equation and we have to solve it, so it is obvious that we will have to integrate this equation 2 times, okay? And after integrating this equation 2 times, we will get the value of x of t. But if you will try to integrate this equation directly, then there will be some problem. So let us follow a very simple trick. To cast this equation in integrable form, we simply multiply this equation 1 both sides by this factor 2 times dx by dt. When you will multiply by the factor 2 dx by dt, the equation will be casted into a very simple integrable form. As you can see, I have multiplied it. This is 2 dx by dt times d2x by dt square plus 2 omega square x times dx by dt equal to 0. Since in RHS there is 0, so even after multiplying by 2 dx by dt, the result will remain 0. Okay. Now, the first term in LHS, this can be written as d dt dx by dt whole square. You can check it. When actually you will differentiate this dx by dt whole square with respect to t, what will be your result? You can see. This will be simply, this is just a function of function, so this will be 2 dx by dt, okay? And then this dx by dt will be differentiated with respect to t, and so that will be d2x by dt square. So instead of that, I have written here d dt dx by dt whole square. Again, see the RHS. In RHS, this omega square is a constant factor, okay? And 2x dx by dt, that can be written as d dt x square. You can check it. When you will differentiate this x square with respect to t, you will get 2x dx by dt, okay? I have written this second term in RHS, so there is minus sign here. Now this equation is in integrable form. So let us integrate this equation with respect to time t, okay? So integral d dt dx by dt whole square dt equal to minus omega square. Since omega square is a constant factor, so I have written it outside of the integral, and d dt dx square dt. Now, as you know, you can see this dt and this dt will cancel out, and this will be simply integral of differential of dx by dt whole square. And as you know, the integral cancels the differential, so this integral will be simply dx by dt whole square, okay? So in LHS, our result is dx by dt whole square. Again here, this dt will cancel out, and integral of differential of x square that will be simply equal to x square. And since it is an indefinite integration, so we must write an integration constant. So in this equation, this c is used for the integration constant, okay? Now, as you know, whenever in our equation there is integration constant, that very integration constant is evaluated by using the proper boundary condition, okay? Proper boundary condition. Now, since there is only one arbitrary constant or integration constant here, so we will need only one boundary condition. So let us consider a boundary condition here. You can see, if this x equal to a, that is, let us say this point is P1 and this point is P2. These are the extreme positions of the particle between which this particle executes simple harmonic motion. So at this point P1, x will be maximum, and that maximum value of x has been assumed a, which is called amplitude of SHM. And at point B, x is equal to minus a. Actually, minus sign here actually indicates the direction. If you write the value in right side of this equilibrium position or this origin, you take the value positive, and in left side you take it negative, okay? And since at x, this x equal to a is the extreme position, so you know at this position velocity of the particle becomes 0, and so that the particle returns back towards the equilibrium position from the extreme position. Similarly, similarly at point P2 also v will be 0, and again from this point the particle returns back to the mean position O, okay? So you can say that when x is x max, and that maximum value is either plus a or minus a. Here both plus a and minus a have same value a, and it is the maximum value of x, which is called amplitude of SHM. And as you know, at this position the velocity of the particle is 0. And what will be velocity? When you say velocity of the particle, that is simply equal to dx by dt, okay? So dx by dt here will be 0. So this is our boundary condition, that our boundary condition is what? When x is either plus a or minus a, then dx by dt is 0, okay? This is our boundary condition. So let us impose this condition in this equation 2. If you will substitute x equal to plus minus a in RHS, then you have to substitute 0 for dx by dt in LHS. So let us substitute it. So you can see from this equation 2, after imposing this boundary condition, our result will be 0 equal to minus omega square a square, because plus minus a square will be simply equal to a square, okay, and plus c. So from here you can see that this c is equal to omega square a square. This is the value of integration constant. Now we will substitute this value of integration constant in this equation 2. Okay. So see this equation 2 and substitute this value of c, which is omega square a square. So after substituting, we get dx by dt whole square equal to omega square times a square minus x square. Actually here omega square has been taken as a common factor. And so that this dx by dt will be equal to omega times a square root of a square minus x square. Actually this is also a very important result, because you know this dx by dt is what? This is velocity of the particle at any time t or at position x. So this is also a standard equation, and it represents the velocity of the particle executing simple harmonic motion at any time t or at a position x. Okay, so you should remember this result too. Okay. Now after one integration, you have obtained dx by dt, not x, but our final aim is what? Our final aim is to obtain x as a function of t. So we must integrate this equation again, and then you will get actually the value of x as a function of t. So before integrating, we have to cast this equation a1 in the appropriate integrable form. So let us rearrange the terms. You can see this equation a1 can be written in this form. This is dx over root over a square minus x square, and that is equal to omega dt. Now this equation is in the integrable form. So let us integrate it. So integral dx over a square root of a square minus x square, this is equal to omega times integral of dt. This is a very simple integral. Definitely you have an idea of it. You know what will be the integral in LHS? This will be simply sine inverse x over a, and the integral of dt will be simply t. And since again it is an indefinite integral, so we have to put some another integration constant. So let us see. Our result is sine inverse x by a equal to omega t plus phi. Here phi is another integration constant. And so that you can say that this x over a will be equal to what? This is sine omega t plus phi. And so x will be equal to a sine omega t plus phi. This is actually the solution of simple harmonic equation of simple harmonic motion. Okay, because we have obtained x as a function of t. And you can see actually in this equation there are two arbitrary constants. One is a and another is phi. And since the equation of simple harmonic motion is a second order differential equation, so definitely in its solution there must be two arbitrary constants. So in this solution a and phi both are the arbitrary constants. Okay, you can check it that is it a valid solution or not. If your aim is to prove that this is a valid solution, from this equation a2 you can find d2x by dt square. You have only to differentiate this equation a2 two times, and then you can see after differentiation you will get that d2x by dt square is equal to minus omega square x. You will get it. I am not differentiating here, but you can do it. And this is actually the equation of SHM. As you know, the solution of any differential equation satisfies the differential equation. So this solution you can check it satisfies that equation of motion of simple harmonic motion. So this is a valid solution. Okay. Now actually in this equation, the value of this x will depend on the argument of this sine function because a is constant. So what is the value of x? And if you know x, after one differentiation you will get velocity. After two differentiation you will get acceleration. So once you know the value of this omega t plus phi, you can determine all the parameters of motion. It means you can find where there is particle, what is its velocity, what is its acceleration. So we simply say that this omega t plus phi, which is argument of this sine function, this completely determines the state of motion of the particle. And you know the factor which determines the state of motion of the particle, that is called phase of motion. So this quantity omega t plus phi, which I have denoted by the symbol delta, this is called phase of simple harmonic motion at time t. Okay, I think you are getting the things. Now, if we consider that t is equal to 0, it means your aim is to find what will be the phase of the simple harmonic motion initially at 0 time. You can see this will be simply equal to phi, and that's why this constant phi is known as initial phase. Why we call it initial phase? Because it is phase of simple harmonic motion at the initial time, that is at t equal to 0. So phi is called initial phase. Actually this phi is also known as epoch or phase constant. Okay. Since phi is the initial phase, that is phase at t equal to 0. But you know, the selection of t equal to 0 is completely arbitrary. When we will take t equal to 0, it depends on the observer. For example, a person can take t equal to 0 when the particle is at the positive extreme position. Or another person can take the t equal to 0 when the particle is at negative extreme position. A third observer can take when t is equal to 0 when the particle is at equilibrium position. Any choice can be made. Okay? That's why we simply say that the value of this phi depends on the reference position where we take t equal to 0. So in accordance with our assumption, taking t equal to 0 at a particular point, the value of phi will be different and all will be correct. So actually, to clarify this idea that how we can say that phi depends on our choice, that is, what is your choice of taking t equal to 0, that decides what will be the value of phi. To clarify this idea, I am taking here few examples. Let us see it. In first example, we consider that we take t equal to 0 when x is equal to 0. It means you are taking time t equal to 0 when the particle is passing through the equilibrium position. Then an observer takes t equal to 0. Let us see what will be the value of phi in this condition. For this, we will substitute x equal to 0 in this equation A2 and t equal to 0. So substituting the value of this x and t in A2, our result will be 0 equal to a sine omega times 0 plus phi. So 0 equal to a sine phi, but as you know, a is not 0 because this is amplitude of simple harmonic motion or the maximum value of displacement. And so that definitely this sine phi will be equal to 0. And if sine phi is 0, that means phi equal to 0. So in this condition, when an observer takes the reference time t equal to 0 when the particle passes through the equilibrium position, such an observer will write phi equal to 0, and so that observer will write the simple harmonic motion is represented by x equal to a sine omega t. So this x equal to a sine omega t, this is also a solution of simple harmonic motion, simple harmonic motion's equation. Actually, in this condition, phi has been taken 0. Actually, this result is most of the time used to represent a simple harmonic motion. Actually, you know, the solution of equation of SHM is also called equation of motion of SHM. You can say that x equal to a sine omega t is the equation of motion of SHM. Okay? Or this equation represents the SHM. You can say. Okay. Now let us take another example. We take t equal to 0 when x is equal to plus a. It means when our particle is at right extreme position, that is at x equal to a, then we consider that t is equal to 0. Now let us see for this reference time what will be the value of phi. Again we will substitute these values of t and x in the same equation, that is x equal to a sine omega t plus phi. Let us substitute these two values. At the place of x now we will write a, you can see it here, and t is 0. So this equation in this condition will become what? This is a equal to a sine phi. Now this a and this a will cancel out and sine phi is equal to 1, and so you can say that phi is equal to pi by 2. So if you will take t equal to 0 when the particle is at right extreme position, that is at x equal to plus a, then you will get phi is equal to pi by 2. And then we will represent the SHM by this equation, x equal to a sine omega t plus pi by 2. And since sine omega t plus pi by 2 is equal to cos omega t, so the SHM can be represented by x equal to a cos omega t. Okay? So you can see in accordance with our convenience, we can represent SHM by x equal to a sine omega t, x equal to a cos omega t. Okay? And there is no difference in any physical discussion. All these equations are equivalent to one another. Okay. Now in third example, we consider that when our particle is at the negative extreme position, that is when x is equal to minus a, then we take t equal to 0. So I have written here, take t equal to 0 when x is equal to minus a. In this condition, again when you will substitute these two values in that equation a2, our result will be what? This will be minus a equal to a sine phi. So again this a and a will cancel out and sine phi will be minus 1. And so that you can say phi is equal to 3 pi by 2, and our SHM in this condition will be represented by the equation x equal to a sine omega t plus 3 pi by 2. So you can see from these examples, it is evident that the value of phi depends on our choice. That is, what is your choice of taking t equal to 0? That will determine the value of phi. Actually, phi is simply the phase of simple harmonic motion at the initial moment, that is at t equal to 0. Okay, and the value of phi may be anything in accordance with our choice of taking t equal to 0 at a particular point. Okay, I think this point has been definitely clear to you. Okay, now till now we have obtained the sinusoidal solution of simple harmonic motions equation. That is, we have obtained the solution of equation of motion of simple equation of motion of SHM in terms of sine function. But it does not mean that that solution is the unique solution. Actually, the solution of equation of motion of SHM is not unique. This solution can be written in different form, and in accordance with our convenience of in the physical problem, we write at different places the different solution. Okay, so let us now see what are the other solutions of this equation of motion of SHM. As you have seen just now, that x equal to a sine omega t plus phi is one of the important solutions of this equation of SHM, which is written like this. This is d2x by dt square plus omega square x equal to 0. But this is just one of the solutions. Okay, actually, at the place of this sine function, you can equivalently write cos function. It means the solution of equation of motion of SHM can also be written as x equal to a cos omega t plus phi. You can write it. But if there is a doubt in your mind that is it a valid solution or not, you can check it or you can explain it. Because you know, any solution of a differential equation satisfies the differential equation itself. So if you say that x equal to a cos omega t plus phi is a valid solution of equation of motion of SHM, just like x equal to a sine omega t plus phi, then this solution x equal to a cos omega t plus phi must satisfy the equation of motion of SHM. So let us check it. You can check. And for checking this, let us differentiate this equation 1 with respect to t. See this equation and try to differentiate it. X equal to a cos omega t plus phi. So from here you can say that this dx by dt will be equal to what? That will be minus omega a sine omega t plus phi. Okay. Again we differentiate it. So the second order derivative, that is d2x by dt square, will be what? This will be again minus omega square a cos omega t plus phi. This is very simple integral, so differential. But you can see the factor a cos omega t plus phi, which I have just underlined, that is equal to x. So at the place of this a cos omega t plus phi, you can write x. So our result will be d2x by dt square equal to minus omega square x. And so d2x by dt square plus omega square x equal to 0. And what is this? You can see this is nothing. This is simply the differential equation of SHM. Okay. So what you have learnt, you can see that our assumption that x equal to a cos omega t plus phi is a valid solution of the equation of motion of SHM is correct. Why? Because in this calculation you have seen, if we consider that x is equal to a cos omega t plus phi, then this solution satisfies the differential equation of SHM. And so that we can clearly say that this x equal to a cos omega t plus phi is also a valid solution of equation of SHM. Okay. So till now we have obtained that the solution of equation of SHM can be written either in terms of sine function or in terms of cosine function. That you can write x equal to a sine omega t plus phi. Okay, this is one of the solutions of equation of SHM. Or you may also write equivalently that the solution is a cos omega t plus phi. Okay, these two are actually the valid solution of equation of SHM, and so we can represent SHM either in terms of sine function or in terms of cosine function. Okay. Now we will see some other solutions of this equation, and for this let us expand the first solution, that is we are going to expand x equal to a sine omega t plus phi. As you know, you have definitely studied in trigonometry that sine a plus b is equal to what? This is sine a into cos b plus cos a into sine b. So using that very formula, we can expand this as x equal to a sine omega t into cos phi plus a cos omega t into sine phi. Okay. And this equation can be written as x equal to c sine omega t plus d cos omega t. You can see I have substituted here c for what? Actually, instead of a cos phi, I have written here c. Okay, and at the place of a sine phi, I have written d. Okay, and so x is equal to c sine omega t plus d cos omega t. Actually, this equation is also a solution of equation of SHM. Okay, this is also a valid solution, and you can check it. If you will again differentiate this x 2 times with respect to t, you will get the equation of SHM. I am not doing that. This is just a homework for you. You can try it. Differentiate x with respect to t 2 times, and then you can see you will get the standard differential equation of SHM. So this x equal to c sine omega t plus d cos omega t, this is another form of solution of the equation of SHM. But what is this c, what is this d, you can now find it, because you have written c at the place of a cos phi and d at the place of a sin phi. So if you will square these two and add, so after squaring and adding, you can see we get a is equal to a square root of c square plus d square. Okay, and when you will divide this d by c, you can see this d by c will be what? This will be a sin phi over a cos phi. A cos phi. A and a will cancel out, and this is tan phi. So you can see that this tan phi is equal to d by c, and so phi will be what? That will be tan inverse d by c. So in this way, in terms of the arbitrary constants c and d, we can express the value of a and phi. Okay. Again, we can expand the another solution of the equation of SHM, which I have written in terms of cosine function. You have seen that x equal to a cos omega t plus phi is also a valid solution of equation of SHM. So now let us expand it, and by the using the formula of cos a plus b. You know, cos a plus b is equal to what? This is cos a into cos b minus sin a into sin b. Using that very formula, you can write x is equal to a cos phi into cos omega t minus a sin phi into sin omega t. Now, at the place of this minus a sine phi, minus, including minus, we can write c. So the second term will be c sine omega t. And at the place of a cos phi, we can write d. And so the first term will be d cos omega t. So you can see when we consider x equal to a cos omega t plus phi as the solution of equation of SHM, then we get x equal to c sine omega t plus d cos omega t. And also when you take x equal to a sine omega t plus phi, even then you get same result. So this is also a valid solution of the equation of SHM. But in this case, we have substituted c at the place of minus a sine phi, and d has been written at the place of a cos phi. Again, if you will square and add, you will get a, and that will be equal to a square root of c square plus d square, which is same as obtained earlier. And in this case, you can see d, sorry, here there will be in fact c by d, c by d. See here. Minus c over d. When we will write c over d, see here, this will be equal to minus tan phi, minus tan phi. Okay, and so phi will be equal to tan inverse minus c by d. Okay, so in this way, this a and phi can be expressed in terms of these constants c and d. So x equal to c sine omega t plus d cos omega t is another important form of the solution of equation of SHM. Okay. Now the most important form of the solution of differential equation of SHM is actually written in exponential form. How we can say that this can be written in exponential form? Because you know that sine theta is actually, yes, sine theta is equal to what? This is e theta e to the power I theta minus e to the power minus I theta divided by 2i. Okay, and cos theta is equal to e to the power I theta plus e to the power minus I theta divided by 2. And e to the power I theta, this is equal to cos theta plus I sin theta. Okay. So, actually, you can see that e to the power I theta is expressed as cos theta plus I sin theta. This is called Euler's formula. So the real part of e to the power I theta is cosine function, and its imaginary part is sine function. So the combination of sine and cosine function can be expressed in this exponential form. That's why we say that the equation, the solution of equation of SHM can be expressed in exponential form. Okay. And for this, let us see. The equation of SHM is what? You know, this is d2x by dt square plus omega square x equal to 0. Okay. Actually, this equation 1, which is equation of simple harmonic motion in differential form, Actually, this equation can be put in operator form by a substitution. And definitely this idea you have studied in your course on theory of solution of differential equation, and particularly in physics in first semester we study this. And for this, let us consider that the operator d dt is equivalent to capital D. And so that this d2 dt square, that is second order derivative, this will be equal to d square. And so that in terms of these operators, this equation 1 can be written as what? At the place of d2 by dt square, we will write d square. And there is x, so the first term is d square x plus omega square x and equal to 0. As you can see, we will take x as a common factor, so this will be d square plus omega equal to 0. Since x is, here x should be written here. So here x is not 0, or you can say that this operator is operated on this. So this d square plus omega square will be 0, and so that you can say d square is equal to minus omega square. So what will be this d? As you can see, d will be a square root of minus omega square. And the square root of minus omega square will be what? This will be plus minus I omega, because I square is equal to minus 1. Okay? And that's why the solution of this equation 1 is written as x equal to a e to the power I omega t plus b e to the power minus I omega t. Okay? Here again a and b are arbitrary constants. You can use c and d instead of a and b here too. Okay? So in exponential form, the general solution of this differential equation defined in 1 is written as x equal to a e to the power I omega t plus b e to the power minus I omega t. Okay? Now, since the value of this x must be real, because it is displacement, and for getting the real value of x, the values of constants a and b must be the complex conjugate of one another. A and b may be complex, but for getting or for the real value of x, the complex values of a and b must be the conjugate of one another. So I have written it here. You can see, in order that the solution may give a real value of x, a and b must be complex conjugate of one another. Okay? So if you take a is equal to alpha plus I beta, where alpha is the real part of a and beta is its imaginary part, then definitely this b must be equal to complex conjugate of a. It means b should be equal to a star. When you write a star, it means complex conjugate of a. And how complex conjugate is obtained? You know, we simply change the sign of the imaginary part. So if the imaginary part is here beta in case of a, then for b imaginary part will be minus beta. So b must be equal to alpha minus I beta. Okay? In the similar manner, we also say that if you write the equation in this form, x is equal to a sine omega t plus phi, or you also write it a cos omega t plus phi, then you can write this solution in this form: x equal to a e to the power I omega t plus phi. Why? Because you know that a e to the power I omega t plus phi. This will be what? This will be a cos omega t plus phi plus I a sine omega t plus phi. Okay, and we can take to express the value of x the real part or the imaginary part. So the real part of this equation x equal to a e to the power I omega t plus phi represents this equation, that is x equal to a cos omega t plus phi, and its imaginary part is represented by this equation a sine omega t plus phi. So when you write the solution as x equal to a e to the power I omega t plus phi, then it represents both of these solutions. So we can express x either in terms of the real part of this function or in terms of its imaginary part. So this is the most appropriate or most general form of the solution of simple equation of simple harmonic motion, x equal to a e to the power I omega t plus phi. Okay, so I think you have definitely understand the whole calculation, how we can obtain the solution of equation of motion of SHM in different forms. And for your convenience, as a summary, I have written all those solutions here. You can have seen that the solution of equation of SHM can be written as x equal to a sine omega t plus phi, or a cos omega t plus phi, or a sine omega t plus b cos omega t, or a e to the power I omega t plus b e to the power minus I omega t, or in the most general form it is written as x equal to a e to the power I omega t plus phi. Okay, so these are the different forms of the solution of differential equation of SHM. Okay, I hope this how we can solve the equation of motion of SHM, which is just a second order ordinary differential equation. Definitely this concept has been clear to you. Thank you very much.